This example has variables instead of numbers. Check how the tangent and normal lines are determined here in differential calculus. There is a pattern in solving for the equations of the tangent and normal lines of plane curves. The first step is to look for the slope of the function by taking its derivative. With a provided point, you surely will be able to find a numerical value for the slope. This parameter is used through different line forms, depending on what complementary data is given. The first format for the line is a slope-intercept form, which is y as equated to mx plus b. This is used when y-intercept is given along with the function. The second line format is the point-slope form, which is y less y1 as equal to the slope m times x less x1. This is used when the complementary data given are coordinates of a point. Both line formats result to the tangent line of the plane curve, so next is to solve for the normal line. With the same procedure, one only needs to change m tangent into the normal slope, which is basically just the negative reciprocal of the tangent slope. Plug these into the line format of your choice and have the normal line function. Take note that we are to look for the slope using derivatives and partner it with those line formats which have slope too. This is the main reason why slope-intercept and point-slope formats are usually incorporated. The function is a squared times y as equated to x cubed, and we are to determine the equations of tangent and normal lines at point AA. With the x and y coordinates provided, we are to use point-slope form y minus y1 as equal to m times x minus x1. The first step is to determine the slope m. With the function a squared y is equal to x cubed, the configuration shows two ways to have y prime. The first is to use implicit differentiation. Having a as a constant, the left side is then differentiated as a squared with the derivative of y with respect to x. This is equal to the derivative of x cubed. dy over dx is y prime, making the function a squared y prime as equal to 3x squared times the derivative of x from chain rule. Dx over dx is 1, making the function a squared y prime is equal to 3x squared. Thus, y prime is then 3x squared over a squared. The other option is to fix the function and continue with explicit differentiation. With a squared y is equal to x cubed, extract out y making it equal to x cubed over a squared. Then take the derivative. dy over dx is then y prime. Then a, being a constant, will be placed before the derivative of x cubed. Y prime is then 1 over a squared of 3x squared. Then multiply the derivative of x as required by chain rule. Again, dx over dx is 1. So we still have y prime as 3x squared over a squared. Next is to look for the slope at a certain point with coordinates a, a. As m is 3x squared over a squared, plug a for x, thus having 3a squared over a squared, canceling out the a's and leaving m as 3. With the slope determined, we can now look for the equation of the tangent using the point-slope form. Substitute coordinates and the slope, and have y minus a as equal to thrice of x less a. Distribute the constant and have y minus a as equal to 3x minus 3a. Arrange terms and have 3x minus y as equal to 2a. This is the equation of the tangent line. Proceed to solving the equation of the normal line using the same point-slope form. However, we are to use the normal slope and not the tangent slope. And since what we know is the tangent slope, use the relationship that the normal slope is the negative reciprocal of the tangent slope. The function then becomes y minus a is equal to negative 1/3 of x less a. Cross multiply negative 3 and get negative 3 times the binomial y minus a as equal to x minus a. Distribute negative 3 to have negative 3y plus 3a as equal to x less a. Arrange terms once again to have x plus 3y as equal to 4a. This is the equation of the normal line.